Section 8.2 video part 2. Sorry about the last video, I didn't realize it cut off. So what is the parent function of each equation below? Describe the translations. If you look at each of these equations and if you want to describe the parent graph, well, you need to look at your a and your b value. Notice they're the same. So my parent graph would be y equals 9 for my a value, my b value is 3 to the x power. So that would be my parent graph. And if I want to describe the translations, my translations are going to be y equals 9 times 3 to the x minus h plus k. So anything attached to x is your h value, anything on the outside is k. So for this first one we have, our h value would be equal to -1 because it's x plus 1. In order to get that plus 1, we have to have x minus -1. Then my k value, since there's nothing on the outside, you can write plus 0 if you want, would be equal to 0. So that means we're moving our graph to the left a value of 1. So left 1. For the horizontal asymptote, you always use your k value. So my horizontal asymptote in this case is going to be y equals 0. If you look at the second example, we have 9 times 3 to the x minus 4. So your h value is going to be 0 because there's nothing attached to x. Your k value is equal to -4. So this graph from my parent graph is translating it down 4 from the parent function. My horizontal asymptote now moved because we're moving our graph down 4. It's going to now be y equals -4. The next equation, we have an h value of 3 and a k value of -1. So this graph is going to be translated two different ways. Right 3 because it's positive 3, and down 1 because our k value is -1. That means that our horizontal asymptote would be y equals -1 because it's always your k value. Now, we have a lot of applications to exponential functions. Modeling the half-life of exponential decay of a situation, we have a half-life formula. The formula for half-life is going to be y equals a times 1/2 to the x divided by h power. So that's an h right there. In this case, a stands for the starting amount or value, and your half-life is what your b value is always going to be for these problems. That's why it's called a half-life equation or half-life formula. X is equal to the time. Normally it's time in years, and h stands for the half-life. And they give you that in the equation. For example, carbon-14 is used to determine the age of artifacts in carbon dating. Its half-life is 5,730 years. Write an exponential decay function for a 24 milligram sample. Find the amount of carbon-14 remaining after 30 millennia. Hint, 1 millennium is equal to 1,000 years. Now for this, we have y equals my starting amount, which is a 24 milligram sample, and my b value is always going to be half because it's a half-life. And then x, we don't know of the time in years, but our half-life, it said right here, was 5,730. So we divide x by 5,730, and that's all as an exponent, so usually it's a good thing to put parentheses around it. Now, this would be my equation for a. Then for B, we want to figure out the amount of carbon-14 after 30 millennia. So first I want to figure out how many years that is. So 30 times 1,000. If I do that, I get 30,000. So that's what I'm plugging into x and for my equation. So if you get out your calculator and we do this, we have 24 times a half, so 0.5. And if you have an older calculator, make sure you put the exponent in parentheses. If it's newer, you don't really need to. So we have divided by, and we're doing 30,000 because that's the year that we figured out for 30 millennium, divided by 5,730 because that's your half-life. And notice I put it in parentheses, enter, and I get 0.636, so I'm going to round that to 0.634. So then after 30,000 years, I would have a y value of 0.64 milligrams. So this is what would be left. Let's do another example. Arsenic 74 is used to locate brain tumors. Its half-life is 17.5 days. Write an exponential decay function for a 90 milligram sample. Use the function to find the amount remaining after 6 days. So the equation would be y equals my starting amount, which is 90 milligrams, times 1/2, because it's a half-life. We're decaying each year by 15%, to the x over 17.5. Now we want to figure out how much is remaining after 6 days. So that means I'm plugging in x value of 6. So if we do this on our calculator, we have 90 times 1/2 to the 6 divided by 17.5. When we do this and hit enter, you get 70.96. So after 6 days, there's approximately 70.96 milligram of arsenic 74 remaining. The next part we're going to talk about is just a little bit off from that. Sometimes we graph exponential functions. One of the graphs asymptotes sometimes will end up being y equals e, where e is kind of like pi, where pi is an irrational number, so is e. So it's an irrational number. And remember, irrational numbers, that means they're not repeating and you can't write them as fractions. So it's approximately equal to the number 2.7182818 dot dot dot. So it goes on and continues forever. So for this, exponential functions with base e are useful for describing continuous growth or decay. So if you look on your graphing calculator, let's find this E button. Just like we have a pi button, notice that underneath the pi button we have E right here. So if you hit second and division, you get your E value, and if you hit enter, that gives you the value of E. You also have it in another place. If you hit second and ln right here, notice above that you have e to the x. So if you want to write it with an exponent, it does that for you. So let's say we want to figure out what e is equal to. Anything to the first power gives you its value, so that's how we would do that. So you can use either of those two. Usually I use the second and then the division symbol. Let's get comfortable using e now. Let's practice plugging this into our calculator. So if I wanted to do e to the 4th power in my calculator, I would just do second division to the 4th, enter. And then I have e, or I could do second ln if I wanted to do to the negative 3rd power. And if I wanted to do e to the 1/2, and if you're doing the 1/2 power, make sure to put it in parentheses, especially if you have older calculator. And we're going to round to 4 decimals when we put this on our sheet. So the first one we had was 54.5982 and 0.0498, and the last one 1.6487. So in Algebra 1, you learn the formula for simple interest, I equals PRT. The more frequently interest is compounded, the more quickly the amount your account grows. The formula for compounding continuously, for computing continuously compounded interest is using the base E. So the continuously compounded interest formula is A equals PE to the RT power. The key words when you're doing this are continuously compounded interest. So A represents the total amount, or total value. P is your starting value, or starting amount. R is your rate, and T is the time. And normally we use time in years. So let's do some word problem practice. Suppose you invest $1,300 in an annual interest rate of 4.3% compounded continuously. Keywords. Find the amount of money you'll have in your account after 3 years. So for this equation, we're using, since it says continuously compounded, A equals PE to the RT power. So A is equal to our initial amount, which would be $1,300, times E, so I should write E there, and E is to the point, and you have to write 4.3% as a decimal, so that would be moving it over 2 places, so 0.043, times our time, which in this case is after 3 years, so times 3. So if I plug this into my calculator, and I don't have to put those parentheses, but I'm going to. So E to the 0.043 times 3. And we end up with a value of, and since we're talking about money, I'm going to round to the nearest hundredth. So we have 0.997, so I'm going to round up to $1,479. After 3 years. So let's do another one. Suppose your parents insist that you invest $100 from your summertime part job, and you find out that Harrington Bank is offering an annual interest rate of 4.8% compounded continuously. How much money will you have in your account after 3 years? So we know compounded continuously, A equals PE to the RT power. So A is equal to 100 times E to the, we need to write the rate, which is 4.8% as a decimal. So that would be 12.048 times 3. So same thing in my calculator. When I plug this into my calculator, notice I get $115.49. Now be careful how you plug these problems into your calculator, because if you plug it in correctly into your calculator, it's easy to get a wrong answer. The next question says, you have a man-made lake in your backyard. You have to put 50 fish in the lake, and the population of the fish is increasing by 8% each year. How many fish will be in the lake after 15 years? So for this one, it didn't say anything about continuously compounded. So if it doesn't say anything about continuously compounding, what formula do I use? Well, if we're increasing by 8%, I know I'm using y equals AB to the x power. So I initially have 50 fish in the lake, so that's my A value. And then if my R is equal to 8% as a decimal, that's 0.08. So remember, to find your, in this case it's increasing, so to find your growth rate, B is equal to 1 plus R. So B is equal to 1 plus 0.08. So that would be 1.08 to the x power. So this is my equation. Now we want to figure out how many fish there are going to be in the lake after 15 years. So y equals 50 times 1.08 to the 15th power, and you're going to want to plug this into your calculator. So when I plug this in my calculator, I get 158.608. But remember, we're talking about fish. So if we're talking about fish, well, we don't have part of a fish. And usually you don't round up when you're talking about population. So in this case, I would say 158 fish after 15 years is how many will be in the lake. Last year, you bought a Kindle Fire touchscreen for $350. The Kindle has a decay factor of 0.90. How much is your Kindle worth after 5 years? So in this case, now we're doing, again, exponential growth. Y equals AB to the x, because it didn't say anything about continuously compounding. And for this, I know that it says I have a decay factor of 0.90. That means that I am using that as my B value. I don't have a percentage there. So Y equals, and I'm starting off with $350 times 0.90 to the x. So if we want to figure out after 5 years, we plug in 5 for x, and then plug this into our calculator. So when you plug that in, you end up with $20.67 after 5 years. I use a decimal here because I'm talking about money. And does that make sense? We start off with $350 buying it, so then after 5 years, if your value is depreciating, that means it's going to get less and less, so that makes sense in the context of this problem. Make sure you bring this with you to class, and we will do more examples of this.